Let's talk about monsters, the kind that truly inspire awe and a bit of fear. Not the ones under your bed or in your closet, but the ones lurking in the vast expanse of the universe, far beyond our world. These are the real titans of terror, black holes. A black hole forms when a massive star, at the end of its life, dies in a spectacular supernova explosion. It's a cosmic firework display, signaling the birth of something truly extraordinary. This explosion leaves behind a core so incredibly dense, packed with matter beyond comprehension, that its gravity becomes inescapable, an irresistible force of nature. Nothing, not even light, the fastest thing in the universe, can escape its relentless pull. It's a gravitational prison from which there is no escape, hence, black. Because no light reflects, no light escapes, it appears as a void against the backdrop of space. Imagine crushing our sun, a star of immense size and power, down to the size of a pebble. The sheer force required is unimaginable. That's the kind of density we're talking about when we discuss black holes. It's a level of compression that defies our everyday understanding. This density creates a gravitational field so intense that it warps space-time itself, bending the fabric of reality around it. Black holes aren't just holes in space, they are so much more than empty voids. They're deep wells in the cosmic landscape, gravitational whirlpools that distort everything around them. They represent regions where physics, as we know it, breaks down, where our understanding of the universe reaches its limits. We can't see them directly with our telescopes. They are truly invisible, but we see their effects on the universe around them, subtle but powerful signs of their presence. We observe stars flung around invisible partners, their orbits distorted by an unseen force. We see jets of energy shooting out as matter spirals in, superheated plasma ejected at near light speed. Black holes are one-way streets in the universe, a point of no return. Once you cross the event horizon, there's no coming back, no escape from its gravitational embrace. They're regions where gravity has won the ultimate battle, crushing everything in its path. This isn't science fiction conjured up in a writer's imagination. It's a direct consequence of Einstein's general relativity, a theory that has revolutionized our understanding of gravity. Black holes play a crucial role in shaping galaxies, influencing their structure and evolution. They even reside at the heart of our own Milky Way galaxy, a supermassive black hole known as Sagittarius A*. They're not just oddities lurking in the distant corners of the universe. They're essential players in the cosmic story, integral to the formation and evolution of galaxies. When you look up at the night sky on a clear, dark night, remember what lies beyond the stars. It's not just stars twinkling in the darkness, and nebulae, swirling clouds of gas and dust, painting the cosmos with vibrant colors. It's also home to these gravitational giants, these silent, unseen rulers of the cosmos. They are quietly sculpting the universe, shaping the galaxies and influencing the very fabric of space-time. Black holes are the universe's most mysterious engines, both of creation, birthing new stars and galaxies, and destruction, consuming matter and shaping the destiny of galaxies through cosmic violence. And they're far more real and fascinating than any monster you could imagine, a testament to the power and mystery of the universe. What happens if you get too close to a black hole? As you approach, gravity's pull grows stronger, and it's not even. The side of you closer to the black hole is pulled much harder, creating extreme tidal forces. This is spaghettification. You'd be stretched into a long, thin strand of atoms. We've seen stars torn apart this way, their remains forming a glowing accretion disk. This disk, heated to millions of degrees, shines brightly in X-rays, a cosmic beacon revealing the black hole's presence. The accretion disk is chaotic and luminous, a final scream from matter before it vanishes. From afar, we see this light. For the matter itself, it's a one-way trip. Each orbit brings it closer, the pull growing ever stronger. It's like a cosmic whirlpool spiraling toward the drain. Here, the laws of physics are pushed to their limits. The real strangeness is just beginning. Now, we arrive at a truly fascinating point in our journey into the heart of a black hole. We reach the event horizon, the black hole's most famous feature, often depicted in stunning images captured by telescopes around the world. It's the point of no return. It's not a physical surface you could touch or bump into, but rather a boundary, a one-way membrane in space-time. It represents the point of no return. Once you cross it, there's no going back. at least according to our current understanding of physics. To help visualize this, imagine the edge of a waterfall, a powerful cascade of water plunging downwards. Once you cross the point where the water begins to fall, there's no paddling back upstream against the current. You're committed to the fall. Similarly, at the event horizon, the gravitational pull becomes overwhelmingly strong. The force of gravity is so incredibly strong that nothing, not even light, can escape its grasp. To escape the black hole's pull from within the event horizon, you'd need to go faster than the speed of light. And as far as we know, that's simply impossible according to the laws of physics as we understand them. Now imagine you're an astronaut bravely venturing towards this cosmic precipice. For you, crossing the event horizon feels surprisingly unremarkable. There's no dramatic shift, no sudden jolt. There's no sign, no alarm to warn you that you've crossed this critical threshold. But to an outside observer, watching from a safe distance, the situation looks very different. They would see you appear to slow down dramatically as you approach the event horizon, as if time itself is bending around you. Your image would appear to fade and redden, a phenomenon known as redshift, as the light emitted from you loses energy fighting against the intense gravity. Eventually, you would appear to freeze at the edge of the event horizon, your image becoming infinitely faint, seemingly frozen in time forever. This is a consequence of time dilation, a mind-bending effect predicted by Einstein's theory of relativity. Gravity warps not just space, bending the fabric of the cosmos, but time itself, causing it to flow at different rates depending on the strength of the gravitational field. So, who's right? Is time really slowing down, or is it just an illusion? The answer is that both perspectives are valid. Both the astronaut and the distant observer are experiencing reality in their own way. It all depends on your frame of reference, your relative position and motion with respect to the black hole. The event horizon is not just a boundary in space, marking the point of no return, but also a boundary in our understanding of reality, pushing the limits of what we know about the universe. Beyond it, within the black hole, the rules of physics as we know them begin to break down, leading to profound questions and paradoxes. It's a veil we cannot see past with our current technology and understanding, a barrier to direct observation. Einstein's theory of general relativity predicted the existence of these bizarre objects, and recent observations, such as the groundbreaking images from the Event Horizon Telescope, confirm their existence and properties. The event horizon marks the edge of the cosmic unknown, a frontier where our knowledge fades and mystery begins. It's where our intuition and our physics begin to fail, revealing the limitations of our current models. What lies beyond the event horizon? What secrets does the interior of a black hole hold? That's the universe's greatest secret, a puzzle that has captivated scientists and thinkers for decades, and it's still waiting to be solved, beckoning us to explore the deepest mysteries of space and time. So, you've crossed the event horizon, that invisible boundary beyond which there's no return. You've taken the plunge into the unknown. What happens next? What awaits you in the heart of a black hole? This is where things get really strange, where our understanding of the universe is pushed to its absolute limits. The truth? We don't know for sure. The interior of a black hole remains one of the most profound mysteries in all of science. It's a place where the known laws of physics seem to break down. General relativity, Einstein's theory of gravity, says everything falls to a singularity. It predicts that all the matter and energy that enter a black hole are crushed into an infinitely small space. An infinitely dense point where physics breaks down. A point where space and time, as we understand them, cease to exist. At the singularity, our math fails. The equations we use to describe the universe simply stop working. It's the end of the road for matter and understanding. It represents a fundamental barrier to our knowledge. But quantum mechanics, the theory governing the behavior of matter at the smallest scales, insists information can't be destroyed. If you burn a piece of paper, the information is still there in principle, encoded in the smoke, the ash, and the heat released. But a black hole seems to erase it, swallowing information whole and preventing it from ever escaping. This clash is the black hole information paradox. It's a deep contradiction between two of our most successful theories. It's a sign that our theories are incomplete, that we're missing a crucial piece of the puzzle. Either relativity is wrong, at least in the extreme environment of a black hole, quantum mechanics is incomplete and needs to be revised to account for gravity, or there's a deeper theory waiting to be found, a theory that unifies gravity and quantum mechanics. The fate of matter inside a black hole, what happens to it after it crosses the event horizon, is one of science's biggest mysteries. It's a question that has stumped physicists for decades. It's not just a curiosity, not just an abstract problem for theoretical physicists. It's a clue to a more complete understanding of reality, a key to unlocking the secrets of the universe. The universe is daring us to solve it, challenging us to reconcile our understanding of gravity and quantum mechanics. And the answer could change everything, revolutionizing our understanding of space, time, and the fundamental laws of nature. Enter Stephen Hawking. In the 1970s, he applied quantum mechanics to black holes and made a stunning discovery. Black holes aren't completely black. They emit faint radiation, now called Hawking radiation. This happens because empty space is a sea of virtual particles. Near the event horizon, one can escape while the other falls in. The escaping particle makes it look like the black hole is glowing, while the one that falls in reduces the black hole's mass. Over eons, this causes black holes to evaporate and eventually disappear. But if black holes vanish, what happens to the information they swallowed? Does it disappear, violating quantum mechanics? Or is it somehow encoded in the radiation? Hawking's idea deepened the mystery, sparking fierce debate among physicists. The fate of information remains one of the hottest questions in science. Let's speculate about what's inside a black hole. Some theories, like string theory, suggest the singularity isn't a point, but a fuzzball of tangled energy, preserving information in a new form. Others propose black holes could be gateways, wormholes, to other universes, or that information is encoded on the event horizon itself, like a cosmic hologram. This holographic principle could solve the information paradox by storing everything on the surface, ready to be released. These ideas are bold, but unproven. The singularity is where our best theories meet and fail. It's the frontier of physics, hinting at a deeper reality. The answer is out there, waiting for discovery. Why do we care about black holes? They're the ultimate test of our understanding, where gravity and quantum reality collide. Studying them pushes technology, inspires awe, and challenges our imagination. Black holes have already led to new discoveries, like gravitational waves, and new ways to explore the universe. Every answer leads to deeper questions about our place in the cosmos. The quest to understand black holes is a quest to understand ourselves. They remind us the universe is stranger and more beautiful than we can imagine, and the story is far from over. The universe is calling, full of wonders like black holes and galaxies. You don't need a PhD to feel awe, just curiosity. The atoms in your body were forged in ancient stars. You are made of stardust. Keep asking questions, keep exploring. The mysteries of black holes are invitations to dream and discover. Every answer leads to new questions. The universe is waiting. So keep looking up,